magnetic field due to an infinitely long coaxial line. Okay. Generally, the coaxial lines are made up of two concentric cylinders. Okay. Now, for simplicity of for the calculations, let's assume the coaxial cable is placed along z-axis. Okay. So here, just consider this diagram. Here, the blue shaded are conductors. Okay. So this one is inner conductor and this one is outer conductor. Okay. And conductor carries a current plus I, and the outer conductor carries a current minus I, or the return current is minus I. Okay. Let's assume the inner conductor is having a radius A and outer conductor is having a radius B, and the thickness of outer conductor is T. Okay. So inner conductor is having a radius A and the inner dimension of outer conductor is B and thickness is T. Okay. Now here let's observe the field of this particular scenario. This one is only the cross section of a coaxial cable. If you make a cross section of a cable, you can see two concentric rings like this. Okay. So here, since it involves two currents plus I and minus I, okay, in order to apply this Ampere circuit law, we have to divide the entire space into four different regions. Okay. First region is within the inner conductor. Just see here, the inner radius is A. If you want to find field at a point which is between 0 to A. Okay. So here the entire carrier the conductor carries current I. Okay. So if you want to calculate only up to this point, only part of current will be taken. Okay. That is the region 1. Outside this, okay, you are having the second region, that is from A to B. This one completely encloses inner current. Okay. That is second region. And third one is the region within the outer conductor, which covers the inner conductor completely and covers part of the outer conductor. That is B to B plus T. The region is B to B plus T. And the next one outside the outer conductor greater than B plus T. Okay. Now, since this one is a symmetrical current distribution, that is circular in nature, let's try to apply Ampere's circuit law here. First, in the region from 0 to A, okay, as per Ampere's circuit law, closed integral of L1 H1 dot TL is equal to I enclosed. That is equal to integral J dot ds. Only the current, the inner current, sorry, here we are having two conductors, okay, two concentric circles. Here the entire conductor carries current I, but we are having a region, small region this. So only part of I is forms the current density, that is I enclosed. Okay. So in order to find the I enclosed, we must use the current density formula, integral J dot ds. Okay. Generally, J vector is J is a vector, current density is a vector, that is current by area. Okay. Here the current is I and area of the circle. Okay. So here it is your inner conductor with the radius A, and here it is the observing region. I mean the Ampere path is this one covers. Okay. So the total area is pi a square. Circle area is pi a square. So J vector is I by pi a square, and it is along z axis. Okay. So I by pi a square AC vector, and we need to find ds, and ds also along AZ. So ds is rho d pi d rho AZ, So I enclosed is integral j dot ds. J is I by pi a square az, and ds is rho d pi d rho az. If you take dot product, you will have I rho d pi divided by pi a square. So I by pi a square integral 0 to 2 pi d rho, sorry, d pi integral rho d rho. Okay. So here rho is the variable, okay, from 0 to a. Okay. So 0 to a. Now let's take only the limits for pi. So I enclosed is I by pi a square. Here 2 pi minus 0, that is 2 pi, and it is rho square by 2. So if you cancel the pi, okay, and 2, you will have I rho square by a square. So the current enclosed by the ampere path 1. Okay, so just go back to diagram. Okay, so here L1 is the ampere path 1, L1, and the current enclosed by this path is fraction of current, and the fraction is rho square by a square. I enclosed is equal to I rho square by a square. As per Ampere circuital law, closed and integral of h dot dl is I enclosed. So closed and integral of L1 h1 dot dl is equal to I enclosed, that is equal to I rho square a square. I rho square a square. Here we know that the carrier is, the coaxial cable is along z axis. So the field will be only in the a pi axis. So you can take the H1, the field in the ampere path L1 is having only the a pi components, having only a pi components. So H1 is H1 a pi, and dl is along the a pi rho d pi a pi. Okay. So close integral of H1 dot dl is integral 0 to 2 pi. This one is H1 a pi, this one is rho d pi a rho. With dot product, you will have H1 rho outside integral 0 to 2 pi d pi 2 pi rho H1. Now 5 and 4 is equal as per Ampere's law. Okay, so 2 pi rho H1 is I rho square by a square. Okay, so from this you can get H1 is I rho square by a square 2 pi rho. Okay, you may cancel one row. Okay, so you will have H1 is I rho by 2 pi a square, and we know that H1 is H1 a pi vector. So the magnetic field within the ampere path L1, I mean within the inner conductor, okay, that is H1 vector is equal to I rho by 2 pi a square a pi for 0 less than equal to rho less than equal to a. So within this region, the field is I rho by 2 pi a square a pi, and the region between A to B, okay, I mean the space between the conductor and the outer conductor. Okay, so here the ampere path L2 completely encloses the inner conductor. So the enclosed current is equal to I, and the H2 dot dl2 is H2 a pi rho d pi a pi. Okay, so if you make a dot product, a pi will cancel, H2 rho a pi, so you will have 2 pi rho H2 is equal to I. Okay, so H2 is I by 2 pi rho. Okay, so in vector form, H2 is I by 2 pi rho a pi vector for the region A to B. In region 3, the ampere path covers entire inner conductor and part of outer conductor. So the total current enclosed will be the inner current I and part of outer current, that is integral j dot ds. Okay, and in the amperes circuital law, closed integral of L3 is H3 dot dl3, that is I enclosed. Okay, so H3 is having component along a pi only. So H3 is H3 a pi vector, and dl3 is rho d pi a pi. If you solve this, you will have 2 pi rho H3. Okay, I enclosed, for that you need I along with j dot ds. Here j is current divided by outer conductor area Az. Okay, so outer conductor area, okay, here we are having inner conductor, outer conductor. Okay, so this is A, this is B, and this is T. Okay, so here this one forms a ring. Okay, here the ring area can be calculated as outer circle area minus inner circle area. Okay, so inner circle is 2 pi, sorry, pi b square, and this one is b plus t. So pi b plus t square. Okay, this is outer minus inner. Pi b square will give the total area. Okay, so I enclosed is I plus interval j dot ds. So I, the current is minus I. Okay, minus I by the area, pi into b plus t square minus pi b square dot ds. Okay, uh, here ds we already know that is rho d pi a pi. Okay, if you make a dot product of these two, you will have I minus I by pi into b plus t square minus b square interval 0 to 2 pi interval rho to b, sorry, interval rho equal to b to rho d pi. Okay, so if you solve this, you will have I enclosed is I minus I into 2 pi rho square minus b square divided by 2 pi into t square plus 2bt, that is equal to I in common 1 minus rho square minus b square by t square plus 2bt. Okay, this is I enclosed. Just equate this one with equation 11. You will get h3 is I by 2 pi rho into 1 minus rho square minus b square divided by t square plus 2bt. Okay, in vector form, h3 vector is I by 2 pi rho 1 minus rho square minus b square divided by t square plus 2bt into a pi. This one is valid from the region b to b plus t. And the last region, which completely encloses both inner conductor as well as outer conductor. Okay, this is the Amperian path. So this one takes minus I, this one takes plus I. So the current enclosed is equal to 0. So the field will be 0. Field will be 0 for the outside the coaxial cable. Okay, so that's why the coaxial cables don't produce any interference with other conductors or other devices. Okay, so as a summary, you can give the field H vector is equal to I rho by 2 pi a square a pi vector for the region 0 to a, and I by 2 pi rho a pi vector for the region a to b, and I by 2 pi rho into 1 minus rho square minus b square divided by t square plus 2bt a pi vector for the region b to b plus t and 0 outside b plus t. Okay, and if you plot the same with the parameters b is 2a and t equal to a. Okay, if you take a b is 2a and t equal to a, if you plot the magnetic field along the pi axis with respect to rho, then you will have a curve like this. Okay, so from origin initially it is 0, it is gradually increases till the edge of the conductor. So at that time the value will be I by 2 pi a. Then after that point it gradually, it suddenly decreases or exponentially decreases. This region can be explained. Okay, so inner conductor is having a constant value. Okay, and outer current will produce a opposing field. Okay, so from a to b the field is opposing and it is in the negative slope. It is in the, already you are having positive value, it is the negative slope. That's why you are having a decreasing slope from the inner conductor to outer conductor's inner boundary. Then from this point, okay, to thickness, okay, so constant, then from there it gradually decreases, and outside the b plus t the value is 0. Okay, so the magnetic field H is continuous at all the conductor boundaries. It is continuous one. There is no abrupt changes, no sudden jump in the H vector. The field outside the cable is 0 because it encloses both inner conductor and outer conductor, which means it covers positive current as well as negative current. And the external field is 0, so the coaxial cable acts as a perfect shield, okay, which will not radiate any field outside the cable.